So now let's look at the characteristic polynomial of a linear operator. So this idea, we got really close to this idea once before when we talked about the minimal polynomial, which is actually closely related. So suppose that lambda 1 through lambda m are the distinct eigenvalues. So distinct eigenvalues of our linear operator T on V, where V is a complex vector space. So in other words, I'm assuming here that F is the complex field. But if not, then we just assume these are the eigenvalues of the complexification, and everything will work out just fine. And let's let dj be the multiplicity of the jth eigenvalue lambda j. Then the characteristic polynomial is z minus lambda 1 to the d1 power multiplied against all the other factors of z minus lambda j to the corresponding power. Okay, so then this guy is the characteristic polynomial of T. Okay, so now this is the thing that in your previous class you found this as the determinant of well, actually I guess I should say matrix of T minus lambda times the identity matrix, right? And then factored. But since we don't have determinants, or since we're following Axler and doing this without determinants, we don't have that yet. So this is the other way to define it. The only problem is we also don't yet have multiplicities. What the heck is this multiplicity? So you can either pretend that you know what I mean, or we can go through the next definition. So if lambda is an eigenvalue of T, or again, or the complexification of T if we're dealing with a real vector space, then we say that V is a generalized eigenvector or sometimes this is called a degenerate eigenvector, depending on how mean your instructor is. Or a defective eigenvector, if they're really mean. If V is non-zero and T minus lambda I to the j power applied to V is equal to 0, for some positive integer j. And so the case j equals 1, if this is true with j equals 1, then that's just a standard eigenvector. So then the generalized eigenspace of T, of T corresponding to lambda is G lambda T, which is actually in here. So let's put this down here where we've got some room to work. So G lambda T, so this is the generalized eigenvectors, and I guess I should say generalized lambda eigenvectors of T, union with 0, because 0 is never an eigenvector, which is the same thing as the null space of T minus lambda I, where we've raised this to a big enough power, namely the dimension of V. At least that's true for when V is finite dimensional. Okay, so then for any linear operator T, we have that V it actually decomposes as the orthogonal direct sum, or sorry, it decomposes as the direct sum. Forget I said orthogonal. It's true, but we don't need it, so forget it. And of G lambda K T, and each G lambda K is invariant under T. So the dream and the hope is that you can find a basis of eigenvectors of T, right, for whatever your vector space is. And then the sad, harsh reality is that that's just not possible. And we've seen examples of when that fails, like when we have nilpotent operators or shears or things like that. A nilpotent operator is an operator that some power of which is equal to 0. And so the example that we saw of that one was this guy. That's sort of our standard operator, or standard example of that. So you can't always get a basis of eigenvectors, but you can get a basis of generalized eigenvectors and a nice decomposition and everything else. So yeah, and maybe I'll write that. So and V has a basis of generalized eigenvectors of T. And so studying that sort of structure really gives you a nice decomposition of T and allows you to understand exactly what's going on. The only thing that we need about that today, however, is multiplicity, right? That's why I started talking about all these crazy generalized eigenvalues. And so the multiplicity of lambda j is the dimension of the corresponding generalized eigenspace.